All right, in this quiz, we're looking at an equilibrium reaction as shown here, and we want to make sure that we're noting the states of these chemical species. We have two gases and one solid, and as we work through this problem, that's definitely going to be relevant for setting up our equilibrium constants. So the first question is asking that if we are at equilibrium already and we have an H2 concentration, what is the methane partial pressure? And here we know we're already at equilibrium, so we don't need to do an ice table or anything like that. We simply have Kp. Here's our Kp expression, the partial pressure of CH4 over the pressure of H2 squared. This is from the coefficients on the chemical equations. We plug in, we already have Kp, and we can solve for the partial pressure of CH4. Pretty straightforward, and key to this problem is recognizing that we're at equilibrium already. This is not a shift to equilibrium. And if we're at equilibrium, we know we have to have some product gas, and this is the amount that will be in equilibrium with that H2. Okay, so now the second question says if we have a certain amount of H2 that's in a container with plenty of the other reactant, the solid carbon, which direction is the reaction going to shift? And here we say there's nothing else other than those two reactants, and we know that it's going to shift to the right. It's an equilibrium reaction, and therefore we know that it's going to need to have both gases at equilibrium. There's none of the product gas right now, therefore we need to shift to the right to create some. Again, no product initially present. Equilibrium is all about having both product and reactant in a certain amount that is defined by the K value for the reaction. Okay, the next part is kind of the challenging one, right? C is a bigger question. We want to know the total pressure at equilibrium based on the initial conditions in the previous question. And this is our ice table problem. Asking for the total pressure is a really great way that maybe a multiple choice question or just, generally is a good piece of information to know, where you really do need all of the individual species pressures before you can calculate the total pressure. And so again, initially we have 0.456 grams of H2 in 2 liters. This allows us to get the partial pressure of the hydrogen. We want to do this whole problem in terms of partial pressure because we have Kp. You could calculate the Kc first, that's part D, and then do everything in terms of concentration, but you're asked to calculate pressures anyway, so the most straightforward way is simply to use partial pressure and the Kp that's given. We get the partial pressure of H2, here is 11.8 atmospheres, and this is what we can use in our ice table. So here we know the initial amounts, we don't need to consider the carbon as it's a solid. We already determined that it's going to shift to the right, so we're going to lose 2x of the reactant for every x of the product that's formed. This is due to the coefficients in the chemical reaction, and here's our equilibrium row. Now, we have Kp. Remember, Kp and the equilibrium expression only applies to a system at equilibrium, for which we now have an expression, and we go ahead and plug these values in. But here, if we try to do our approximation, try to say, well, 2x is insignificant compared to 11.8, we're actually not going to be able to succeed. And so perhaps you went through that, and that's a good exercise to do. But what you'll find is that we need to solve this quadratic equation here, and we end up getting the following answers. Now, there are a lot of ways to solve the quadratic. I'm going to show a method at the very end, but for now, I wanted to continue this ice table solution going because with these x's, we now are not quite done, but we have solved for the unknowns in these partial pressures. Now, there's two answers. Either of these is going to make the quadratic true. However, only one of them is going to ensure that both the partial pressures are positive, which they have to be in order for this to be a suitable solution for this particular problem. And the one that works is the lower one, because the one that's 8.8 would be too large and it would make the H2 concentration negative, or rather the H2 partial pressure negative. So this is our solution. 3.952 is equal to x. The pressure of CH4 is therefore going to be equal to, as shown here, the pressure of H2 is simply x, and so it's that solution. And the total pressure, which gives our final answer, is going to be 7.848 atmospheres, which we get from simply adding the two gas pressures together. Okay, the last part is to calculate Kc, and this one is actually pretty quick. remember that equilibrium constants in terms of concentration, Kc, are directly related to equilibrium constants in terms of partial pressure, Kp, and we use the following formula. We know that the change in gas moles here is -1. We go from 2 moles of gas to 1 mole of gas, so that's a delta Ng of -1, and we go ahead and rearrange, plug in, and we obtain a Kc value equals 27.4, and that was the quiz. I did want to return to that quadratic because this is where we sort of left off and I just provided the solutions, and I really think that a graphing solution is a really great one to use. You can distribute, re-isolate, set equals 0, and make the quadratic formula work for you, and you'll get the exact same answers. However, I think this can be more straightforward and avoids a lot of algebra as long as you're confident in your solution. So the first thing we do is we subtract the 0.262 to set one side equal to 0. And now we're going to plot y equals the right side as opposed to 0 equals the right side. And that gives us a graph that looks like this. And now this is so useful because wherever y is equal to 0 here, and that is along the x-axis, wherever that's true, we satisfy the second equation here. And when we do that, we find that there are two roots, and these are the roots that we have solved for in the previous example, or rather the roots that we showed were the answer, and this is how graphing is used to get those roots.